SIA Philomen Raj, MSc, MPhil PhD, retired head Department of Physics, Madras Christian College, Tambaram, Chennai. He is presently serving as a guest lecturer in Loyola College, Nungambakkam, Chennai. He has a teaching experience of 35 years in Madras Christian College for UG and PG students. His field of research is nuclear physics, and he has presented about 30 papers in symposia organized by Baba Atomic Research Center, Mumbai. He has guided 50 MPhil students and about 100 MSc students in their projects. He has authored practical physics books for MSc and BSc courses. He is presently engaged in writing a book on nuclear physics for Printers Hall, India.
Welcome to UGC lecture series in physics. We shall continue with the nuclear and particle physics. Last class we were discussing about Weizsäcker mass formula and we worked out few problems. Today we will be covering Coulomb energy of a nucleus and we shall work out one or two problems. When you say Coulomb energy of nucleus, within the nucleus there are protons. Of course, we have got neutrons also, but protons are positively charged particles. Therefore, there will be Coulomb repulsion and therefore they will be repelling, going away from each other. Hence, there will be Coulomb repulsion and also Coulomb repulsive energy. Therefore, we want to calculate what is the repulsive energy or Coulomb energy inside a nucleus. So, consider a nucleus of mass number A and atomic number Z. So, the atomic number decides the number of protons and therefore, it decides the total charge. So, the charge will be Z into E. What is that E? E is electronic charge. Of course, the proton has got the same charge as the electron. So, the charge is Ze. The R is the nuclear radius. Now, we want to just see how do you get the Coulomb energy. So, we are just considering the nucleus to be made up of many shells. That is, the total radius is R, but it is made up of concentric shells of radius R, small r, where small r is a variable. Now, we consider a sphere of small r, radius small r inside the nucleus. Now, we want to add up one charge, one small shell onto that, shell of thickness dr. So, you have got the shell of thickness dr. So, we want to add up that thing. So, some energy is required to add up because it is repulsive. So, we will just see what is the energy required to add up the shell of thickness dr. See, this is dr, shell of thickness dr onto the smaller sphere of radius smaller. Then add another shell. Finally, we will be getting the total nuclear sphere. So, this part is done by integration. Consider a small sphere of radius smaller, concentric with the sphere. Now, we consider a shell of thickness dr, which I already told you. Thickness dr is added onto that, this one added. So, the energy required to add this shell will be, let us call as dE, the total energy will be E. Now, since we are going to talk about small thickness dr, we are just saying energy is dE. The total Coulomb energy is obtained by adding many such shells of, see, the small radius r will go on increasing and finally we will get capital R. So, you add up all the shells, we get the total energy. So, how will we calculate now? So, let Q1 is the charge that is held by the sphere of radius small r and 4 by 3 pi r cubed into rho. So, 4 by 3 pi r cubed is the volume of the small sphere and rho is the charge density. Now, what is this Q2 now? Q2 is the charge in shell of thickness dr. So, already in the previous thing we saw. So, here this is Q1 and here this is Q2. Here we have got the charge Q2. So, what will be this charge now inside the shell? So, I have to just for that I have to see what is the volume of the shell. See, for a sphere of the surface area will be 4 pi r squared into thickness dr, that will be the volume. See this part, 4 pi r squared will be the surface area of the sphere and dr is the thickness, so that will give the volume of the shell. So this part 4 pi r squared dr gives you the volume and rho gives the volume per, that is charge density, charge per unit volume. Therefore, we get this will be Q2 will be the charge. Now what is the Coulomb energy in adding this small shell dr onto the small sphere of radius r? So I have to just, it like two charges, one is Q1, other one is Q2. So Q1 Q2 by 4 pi epsilon 0 r, that is the basic Coulomb law, Q1 Q2. Now already we have seen what is Q1 and what is Q2. So we are just substituting those values here, namely what we are substituting here, equations 1 and 2 are substituted in this equation 3. See this part 4 by 3 pi r cubed rho, and this is 4 pi r squared rho dr by 4 pi epsilon 0 r. This is for Q1 we have substituted, for Q2 we have substituted, and we get this final result here, dE. So we simplifying, we get 16 pi rho squared r to the power 4 dr by 3 into 4 pi epsilon 0. So this is the energy. So this is the energy required to add that shell of thickness dr onto this sphere of radius small r. Now we have to add many such shells. So when you are adding up many such shells, mathematically it means we are integrating. So we will go to the next part as integration. So the total energy, Coulomb energy of the nucleus will be 0 to r, because the shell, already in the previous thing we saw, see the shell radius, the small r, that is a variable, changes from 0 to capital R. So the integral limits will be 0 to capital R. This dr is a variable thickness, r is a variable. So now we come to this integration part. So 0 to r, and from the previous equation we have just substituted this one. This one is substituted from equation 4. See the equation 4, it is just substituted there, and we get 16 pi squared, equation 16 pi squared rho squared r to the power 4 dr by 3 into 4 pi epsilon 0. Now we are yet to integrate. Now we have to integrate this r to the power 4 integral, all these things are all constant, 16 pi squared rho squared constant, 3 constant, 4 pi epsilon 0 constant. So it is only integral r power 4 dr. So integral r power 4 dr will be r power 5 by 5. Okay. So and the upper limit is capital R. Therefore we get this part, upper limit minus lower limit is 0. So we get r power 5 by this part we get. This is equation 6. Now that rho, what is that rho? We said it is charge per unit volume. Now what is the charge held by the whole sphere, a whole nucleus? It is Ze. So this is the charge held by the nucleus. And what is the volume of the nucleus? 4 by 3 pi capital R cube. Understand? For the total charge held by total volume. So this is charge density rho. Now we can easily substitute this rho into this equation 6, and we will be getting the almost final result. We will just see. So using 7 in equation 6, so we get 16 pi squared r to the power 5 3 4 pi epsilon 0 to the power into 5, and this part is rho, substitute for rho squared, Z squared, but this part we get rho squared. Now we can just simplify that, and finally certain things will get cancelled, and finally we get 3 by 5 Z squared E squared by 4 pi epsilon 0 capital R. So the Coulomb energy is decided only by the atomic number Z, this one, and the nuclear radius R. Why I am saying that? Other parameters are constant. See, we get 3 is constant, electronic charge E is constant, 5, 4 pi epsilon 0, they are all constant. So, the variables are only Z and R. So, the Coulomb energy depends on the atomic number, that is number of proton, and also the nuclear radius. So, equation 9 is the expression for Coulomb energy, inside a nucleus. Now, R we are writing R again already in the Weizsäcker formula. We saw that under liquid drop model, that radius is nothing but radius is proportional to a power 1 by 3, or R is equal to R naught a power 1 by 3. Therefore, see, instead of this R, nuclear radius R, we are just substituting this part, R naught a power 1 by 3. What is this R naught? Is radius constant. We have already seen in the first one or two, first and second lecture classes, we have discussed this. That is only basic. So, this nuclear radius R is written in terms of this. Now, why we write this way? Now, the Coulomb energy is a function of Z and A alone. See, all other things are constant because R naught is also a constant. Therefore, we are writing the Coulomb energy in terms of the two variables Z and A. All other things are constant. This is R naught is radius constant. That will be around, already we discussed that, it will be around 1.2 Fermi. It is not a universal constant, slightly it will change, 1.1 to 1.4 Fermi. What is that Fermi? Fermi is 10 power minus 15 meter. Why is that? Why that small variation? Because the binding energy is not constant. The binding energy is slightly varying. The intermediate mass nuclides will have a greater binding energy, whereas very light nuclei will have less binding energy, and also very heavy nuclei have got less binding energy. Therefore, there is a small variation in binding energy or variation of the how close the nucleons are, and therefore, R naught also slightly changes from 1.2 to 1.4. Now, we will just go to the next one. We are giving the reason. Already what we said, we have given in writing, R equal to R naught a power 1 by 3. This equation 10 already we have discussed or used in Weizsäcker mass formula. There we did not derive, or even Weizsäcker did not derive that. He gave this empirical, he gave us a constant. He found out this is a constant. That constant he found out from experiments. See, what is that Weizsäcker formula? It is mass formula. To finding out the formula for finding out the mass. How we got this constant? These constants were obtained from the experimental mass. From the experimental mass, they found out the constants. There are 5 constants which appeared in Weizsäcker formula. So, we require 5 equations or 5 experimentally known masses, and they found out the unknown constants, and it turned out to be that 0.595 MeV. What is that Cc? Coulomb constant. I am just only because this part we did in Weizsäcker formula. Therefore, we have to just recall. This is Bc is binding energy due to Coulomb energy. Binding energy or binding nature due to Coulomb energy. How can it be? Binding is attractive, Coulomb is repulsive. That is why we get the negative sign here. So, it is a binding energy due to Coulomb factor. It is a negative quantity because of the Coulomb energy presence of protons, the binding energy decreases. That is why you get the negative sign. The Cc refers to there in Weizsäcker formula Coulomb constant, that is the constant due to Coulomb energy. this is Cc. So here we get this equation here. So why I am just saying this, see there in Weizsäcker formula, Bc was this part, is a constant z squared a power minus 1 by 3. There only experimentally he found out, Weizsäcker found out and is given. Now we will just go back to this equation, the previous one. 10 and 11 are very similar. See, we take 10, there also we get, see, this 3 by 5, 4 pi epsilon 0, E squared, R naught, all of them are constant. So I can write E, this energy, as Z squared by a power 1 by 3. Or I can write energy E as some constant Z squared. If you take this A to the numerator, a power minus 1 by 3. That is what we find in this equation. See, equation 11, that is what we find. Bc, that E, the energy E, Coulomb energy E, now it is written as binding energy B in Weizsäcker formula, and therefore a negative sign is included, and this Cc we get. Now what is this Cc? He found out to be 0.595. Now we can even check up that Cc should include what? Say here, this part, equation 10 if you go, what must be Cc? Leave out Z squared and a power 1 by 3. What is left out is the numerator 3, E squared, denominator 5, 4 pi epsilon 0, R naught. If you take this, calculate, I must be able to get 0.595. If I am getting, then it means the Weizsäcker formula is also valid. Say 0.595. Now we will just check up in the next one. The Coulomb energy, we are just calculating the Coulomb energy of aluminium 1327. 13 is the atomic number of aluminium and 27 is the mass number of aluminium. Already we have written Ec is equal to Cc Z squared by a power 1 by 3, and this Cc is 0.95. We saw it in the previous one, 0.595, and if you substitute 0.595 and the atomic number of aluminium is 13, so 13 squared, and mass number of aluminium is 27, so 27 power 1 by 3. So I will be getting 0.95 and 13 squared, 13 into 13 will be 169, and 27 power 1 by 3, cube root of 27 will be 3. So if you substitute, I am getting 33.518 MeV. So this is the Coulomb energy of aluminium 27. Once you know this formula, we will be able to calculate the Coulomb energy of any nucleus. So if you go for a higher, bigger nucleus, see what you are getting, Z, say the Coulomb energy is proportional to Z squared. So as the Z increases, the Coulomb energy, repulsive energy goes on increasing. That is why we are not able to get a very big nucleus. Big nucleus will have a Z large. Therefore, Coulomb repulsion will be large. Therefore, they become unstable and they undergo fission. That is what we get the fission by plutonium nucleus, uranium, etc. You do not get the fission of calcium. Calcium will not undergo fission, or oxygen will not undergo fission. Only heavy nucleus undergo fission because this Coulomb energy plays a role. Coulomb energy is proportional to Z squared, and the atomic number increases, the Coulomb energy increases. What I just discussed, we are putting it in words. So for aluminium 1327, Ec is equal to 33.518 MeV. Now what is the binding energy? Why I am just talking about binding energy here? This is Coulomb repulsive energy 33 MeV. If the binding energy is smaller, then the nucleus will not exist at all. The binding energy must be greater than the Coulomb repulsive energy. Only then it is held together. If both are equal, it becomes unstable, like fission will occur. And if binding Coulomb energy becomes larger, they will separate with large force, large separation, large energy. Now for aluminium, the Coulomb energy, repulsive energy is about 33 MeV and binding energy is 216 MeV. Therefore, it is held because the binding is larger, binding is attractive. Attractive is larger than this repulsive energy. Therefore, it is held together. That is what we are trying to say. If we take uranium, this EC, Coulomb energy, will be greater or almost equal to this binding energy. In that case, it becomes very unstable. Unstable for uranium, unstable, almost equal. So, if you give slightly, if you disturb, they will separate. Slight disturbance will separate. And how do you give that separate? How do you disturb that? In a reactor, nuclear reactor, how do they do that? By bombarding a neutron. Just they send a neutron. When the neutron just enters the uranium nucleus, it undergoes fission, unstable. Suppose I take aluminium and I want to make it undergo fission. Then what is the energy required that I have to give? See, this is already 216 and this is 33. So, more than maybe 180, about more than 170 or 180 MeV I have to give in order to separate. Whereas, if you take uranium, it will be almost equal. This Coulomb energy and binding energy will be almost equal, and it is possible to make it undergo fission. Now, this binding energy, how we obtain this way? Say, you remember before we did Weizsäcker formula, we discussed this. Binding energy per nucleon is about 8 MeV. Binding energy, it's an experimental fact. Binding energy per nucleon is 8 MeV. 8 MeV per nucleon. So, 8 MeV. Now, here this, what is this 27? For aluminium, the mass number is 27. So, 8 into 27, 216. That is what we get, 216. So, the system is bound, what we discussed here. Why it is bound? Because this binding energy part is greater than the repulsive part. So, the system is bound. As the nuclei becomes bigger and bigger, A and Z increases. See, A and Z increases. Binding energy is proportional to A. Binding energy is proportional to A. Coulomb energy is proportional to Z squared. Already we discussed the previous thing we got, say Z squared. The Coulomb energy is proportional to Z squared. Therefore, the Coulomb repulsion increases rapidly. Why do you say rapidly? So, the binding energy increases in one order, A in only first order of A, whereas the Coulomb energy increases with the second order of atomic number, Z squared. When you say Z squared, it will become square of the number. Therefore, it will increase more rapidly. So, this one is linear, the other one is parabolic. So, it becomes a faster variation. Therefore, Coulomb repulsion increases rapidly. This decides the size of the nucleus. So, we may wonder why we get only uranium, plutonium. After that, there is no nucleus available. In nature, we have got up to uranium. So, after uranium has got Z equal to 92. There it becomes unstable, after that you do not get. After uranium, we have got 93, neptunium, other things. Those things are called transuranic elements after uranium. They do not exist in nature naturally. By artificial bombardment, they are produced and they disintegrate. So, this decides the size of the nucleus. That is why we get the size. So, as you go on adding Z, more and more repulsion will be there, and the nucleus cannot be bigger than that because of the Coulomb repulsion. So, the nuclear force, the attraction, binding energy, attraction, that is all short ranged. Within 1 Fermi or 2 Fermi, they are able to attract. Each nucleon is able to attract only its immediate neighbors. Therefore, they are short range, whereas the Coulomb energy is long range. Therefore, what happens is we get the Coulomb force and this one, they both decide together. So, this decides the size of the nucleus. So, in this lecture, we discussed about the Coulomb energy of the nucleus, and we obtained the expression which is very analogous to what was obtained by Weizsäcker, and we have just calculated the binding energy of one nucleus, namely aluminium, and also we have decided we have just said what decides the size of the nucleus. So, the nuclear Coulomb force and binding energy both decide the size of the nucleus. Now, we will have just a few questions. Calculate the Coulomb energy of uranium 92-238 in MeV. Already we have got written the expression for Coulomb energy, and there we get Z coming into picture. Z here it is 92, Z is 92, and mass number A is 238. So, you calculate, find out what is the Coulomb energy of uranium. Why we just said uranium? Because you will know that the Coulomb energy is large, that is why it is unstable and it is suitable for nuclear reactor. So, calculate the Coulomb energy of using Weizsäcker formula. Okay, the same thing, direct here and also using Weizsäcker formula. Why are transuranic elements unstable? So, what we said is transuranic after uranium what we get is the elements after uranium are called transuranic elements, and here even for uranium the binding energy, the Coulomb energy and binding energy are almost same. So, if you go beyond that it becomes unstable, therefore, they are unstable because of the Coulomb repulsion that exists. So, we shall continue in the next class. Thank you.